All right, so our second speaker is David Nadeau. David and I worked at Ethoca. David still works there. I recently left, but I helped hire David. He's one of the best, most passionate junior devs I've ever had the pleasure of hiring, and he has a strong interest in Haskell and everything programming. So he gave a fragment of this talk at Ethoca about a month ago, and I encouraged him to come out and give it here because I thought it was great, and I think this community will appreciate it a lot. So let me hand it over to David.
Perfect. You can use this. All right. Thanks for the introduction. So like Sean said, my name is David Nadeau. I'm a software dev at Ethoca. So in my day job, I'm mostly a JavaScript programmer. But in my free time, I like to explore new technologies, functional programming in particular lately, and just concepts that kind of arise there, since that seems to be the trend. They kind of show up there, and then years later, we see them over in Java. So it's kind of nice to fast forward that progress and learn them when they actually come out. So I'll talk a little bit about testing, unit testing, TDD. Do you want to use it? Can you guys hear me, or should I use this? Okay, cool. Here we go. So I'll talk a little bit about TDD and unit testing just to kind of set a reference point, and then I'll dive into the exciting world of property-based testing, which kind of changed the way I look at testing code and kind of brought some spark and enjoyment back to it. So, why do we test at all? So obviously we know it reduces bugs. It's a relatively easy process, although it's tedious. And the overhead is really small compared to formally verifying our code. Although that is necessary in some industries, it's definitely not necessary in web applications or simple backends for social medias and these kind of apps. But we still have tons of bugs in production. We have, on average, 1 bug for every 100 lines of code. And there was actually a study done in 2013 by Cambridge, and they said that bugs cost the global economy over $300 billion. So maybe there's a problem with the way that we're testing our code. So why not formally verify our code? So Dijkstra is famously quoted saying, program testing can at best show the presence of bugs, but it can't actually prove the absence of them. And then he wrote a textbook, and in that book he states, none of the code in this book has actually been tested by a machine. So he clearly looks down on the fact that we're testing code with a machine instead of proving it. But does he really have a point? If we look at how testing is really utilized, the point of software is to generate revenue in the real world. So bugs cost in the US economy about $60 billion in 2002, and software produced around $200 to $240 billion. So that's roughly 25 to 30% of the cost. So a method that promises to eliminate 100% of bugs would have to cost less than 25 to 35% of the cost of actually running the software. Otherwise, it's not viable, and business isn't going to choose to do it. So how much more does it cost to actually verify our code? So there's a French computer scientist, Xavier Leroy. He verified a C compiler. And the compiler was about 4,500 lines of code, and the verification code was over 35,000 lines of code. So that's around an 8-time scale from verification to code. So we assume that the cost of the software would be roughly the same. I mean, that's a lot more than the 25 to 30% that were allotted. So testing's not going anywhere. Formal verification is just too complicated and takes too long for us to even consider at this point. So we have unit testing. So pretty simply, there's 2 main ways to test a unit of code. You can use a black box method, where you simply say, this is the expected result, here's some edge cases I can consider, and you test those edge cases. There's also white box testing, where you actually look at the structure of the code. You make sure that all the conditionals are actually executed in your testing. You can use the structure of the code, like recursion, to test the base case, the general case, and these kind of concepts. So a little simple example of a black box test. Let's say we have a function. It simply returns the maximum of 3 integers. So let's identify some areas of failure. So all 3 values are different. All 3 are the same. 2 values are equal to the maximum, or 2 are equal to the minimum. So let's run a test for each of those. Looks good. Our code's ready for production. Well, actually, this was the implementation. And in a black box method, we would never have seen that. And it's hard to see initially, but we haven't considered equality. So if the first two values are the largest and the third is the smallest, let's pass in 6, 6, 2. We're going to get 6 is not greater than 6. Once again, 6 is not greater than 6, so return 2. So this code isn't going to work. So obviously we should use, if we're allowed to, the actual implementation of our code to our advantage and not ignore the implementation. So a simple white box test, like I said, explore all the conditionals, pay attention to boundary conditions. And if a function is recursive, that's ideal. We can simply test the base case, the single case, and the general case. So here's a simple example, which is actually pretty good coverage of our simple get-evens function here. So empty list, one item positive, one item negative test, and then a multiple item test. So I mean, that seems pretty good. We got pretty good coverage. It wasn't too difficult. What's the problem? Why do we need to think of a different way to test? So here's a simple scenario. Imagine we have a contractor, and we want him to write us a piece of code giving him only our test. So let's have him write us a simple addition function. There's a nice test. 1 and 1 should be 2. He gives us back 2. I mean, it passes our test, good enough. So let's try and trick him up though, and get him to actually write us an addition function. Let's say -1 and 4 should be 3. Well, he just adds another conditional. So let's add one more. I mean, he's not going to do it again. This guy should be repeatable. I mean, hopefully we've hired a good contractor. And to no fault of his, he just adds another conditional. And that's what TDD kind of is when you take it out of context. Obviously, there's the unmentioned step of don't be an idiot. But if you follow the first 3 rules of TDD to its T, you could do this, right? The minimum amount of code that makes your test pass, right? The minimum, amount of tests to continue writing code. So unless we want to have a test for every single valid input to this function, there's got to be a different way. And actually, what if we just randomly generate the inputs to our test? Now there's no way he can simply just have conditionals for these tests. He's going to have to account for each step. But we've kind of tricked ourselves up here because in this situation we don't have an addition function, so we can't actually write our test without the addition function if we randomize the input. So how can we have this idea of randomized input without actually calling the function itself? And that's kind of where property-based testing comes into play. So what is a property? It's a high-level behavior of a unit of work, or one of our functions. So as opposed to thinking about our code and our testing in terms of, here's some input, I expect this result, it's more thinking, what condition is always true for my function? Regardless of the input, what are the invariants that I can talk to, and just generate any kind of input and expect that these will hold true. And luckily for us, some people in the Haskell community noticed that this was an interesting thing, and they wrote quick check. And Scala community was pretty quick to pick up on it. And it's one of the best implementations of the quick check library. And it's called Scala check. And it's actually a very good and thorough implementation. It does a lot for us. So the basics of Scala check are you simply define a property to test, and then you let it generate the input. And it'll test, by default, 100 random inputs and verify that your condition holds true for all these properties. It does interesting things, like it'll test boundary conditions initially right away, so like max int, min int, these kind of things. It'll try and fail your test as soon as possible. The one part where it kind of gets complicated is it can't generate data for your own custom types, obviously. So you can write your own generators simply using primitive types. So I won't go too much into creating custom generators today. There's a lot of references on the internet, and I'll point to some good ones later on in the talk. But let's walk through a simple example of property testing our addition function. So, I mean, there's a couple ways to get full coverage of addition with properties, but this is a pretty simple way. So for any input, I expect that my addition function will be commutative. So obviously, the order that you add numbers in doesn't really matter. It should be associative. The brackets, the parens don't really matter. The identity of an addition function is obviously 0. And the successor property should hold true, in that given a value, the successor is the smallest value larger than that value. So right away, just by putting these couple lines of code, we now have 400 unit tests, essentially. And every time we run them, it's going to generate different inputs for these. So one of the main criticisms against unit tests is, if we write them first, sure, that's good, but after we write them and run them once, very rarely do they find bugs later on in the future. Generally, it finds them at the start, and then other than regression, they're pretty useless, other than a sanity check. But property tests will actually generate different input every time. So you can actually gain value the longer you run your test. It can keep finding bugs in your system. So it can be really useful in that sense. So like I said, it's a much different way to think about code. If TDD makes you think before you write, property testing makes you think a lot harder. But those properties weren't too useful to us. A lot of people aren't writing math functions in their day-to-day. We write practical code usually. So how do we find valuable properties that are actually applicable to the code that we're writing? So it can be kind of difficult. Luckily, the Microsoft community is surprisingly forward-thinking in this one, especially the F# community. So Microsoft released a list of common patterns that they use for what they call parameterized testing, because they obviously have to have a different word for everything, being Microsoft. And there's a guy who has an F# blog, and he wrote a nice summary of these papers. He gave them all pretty interesting names. And these are kind of high-level properties that most people will be able to identify with in their day-to-day code. So let's kind of step through some common properties. So this is the different path, same destination. So kind of like the commutative property of the addition function, it doesn't really matter which order you do it in, it results in the same output. So here's a simple example. If I have the maximum integer value and I add it to the front of a list and then I sort it, that should be equivalent to simply sorting the list and adding the maximum integer value to the end of it. So now we can test that this holds true for any randomly generated list of integers. So it has this quantifier here. I didn't really explain that for all. And that will just simply generate any valid input for this integer range. We have the there and back again property. This is actually the one I find the most benefit in. It kind of works more like an integration test than a unit test, since it generally identifies two functions together. So if you have a function and there's an inverse operation that you can apply on that function to get back the original, this works really well. Or even simple structure checks, like if I want to insert a value into a structure, I expect that it contains that value. So I can write a nice sanity check saying for any, so if I insert something into that structure, it should contain it. Encryption decryption is a really nice one. If I encrypt a value and decrypt it, I should obviously get back the original. Deserialization, serialization, these work really well. So this one's kind of a nice practical one. Some things never change. So kind of properties that are preserved after a transformation. So like a map operation shouldn't really change the size of a list. Sorting a list shouldn't change its size. And sorting a list shouldn't change its content either. So these are kind of like nice sanity checks to make sure nothing's going wrong in our system. And there's a lot of places you can use this one as well. The more things change, the more they stay the same. So after you apply an operation once, it shouldn't change by applying it once again. So these are all of our idempotent functions. So like sort, once a list is sorted, it doesn't matter how many times we sort it, it remains sorted. Same thing for the filter operation, and I have these kind of reducing functions. And hard to prove, but easy to verify. So it's hard to prove that your prime factorization works for all integers, but it's easy to verify that for these given integers, we can see that, you know, all the factors were prime, and if I reduce the list, I get back the original value. And a nice little picture here of a little puzzle. It's kind of hard to prove what the correct way to solve this is, but given the correct solution, it's very easy to check that this is, in fact, the correct way through the maze. So this one I find a little bit more abstract. I haven't really found any situations to use this one in, but it's still pretty useful. And this is one that people can use right away without thinking too hard about. So it's kind of like the idea I talked about before on we would need a second addition function to test that randomized addition input. And a test oracle is exactly that. It's when you have an algorithm, and let's say you want to refactor some legacy code, and your new implementation should be equivalent to the legacy code. So you can easily just run it through this function. Or an example like a really optimized algorithm, you want to test it against a more brute force slow algorithm, you can use this as a nice sanity check. So yeah, these are really useful, and they kind of begin to behave more like integration tests at some point, which is okay. So one example of a test of like kind of an integration would be if you have a bank and you have intra-bank transactions. It doesn't matter how many intra-bank transactions occur, the total money that the bank has should remain the same. And these are kind of system-wide tests. So here's a little bit of an example with just some situations that we deal with at Ethoca. So very briefly, I'll just explain what Ethoca does so this makes a little bit of sense. But let's say a fraudulent transaction happens at a merchant, then a lot of times it gets through the merchant, they don't really know about it. So it gets all the way through down to the issuing bank, and then the issuing bank actually has better credit card fraud detection. So they detect it as fraud, but because of bureaucracy and lots of reasons, they can't really get it back to the merchant in a fast enough time. So they send us that information, and we send it off to the merchant. So you can see our business model is essentially taking in transactions from the bank that are confirmed fraud, and then alerting them the correct merchants. So we can apply the more things change, the more they stay the same principle to our business logic, which is given a list of transactions, it doesn't matter how many times we apply our business logic on it, it should always return the correct amount of, the same amount of alerts. So applying it once should be the same as twice. Obviously, due to PCI compliance and things like that, we can't be storing credit card information in a database. So we want here, we can test our encryption and decryption. A nice something's never changed sanity test is that if we generate, so this would be a custom generator, so we can have transactions which would be invalid and valid. We could have valid transactions, which would be a curated list of only valid transactions. So we can assume that given a list of valid transactions, it should create that amount of valid alerts. And some things never change, once again, for invalid alerts. Given a list of invalid alerts, we expect no alerts to get created. And a test oracle, let's say we had some legacy business logic, you just want to test that. The alerts that are being returned from this are equivalent to the alerts that are being returned from our awesome new business logic. So I mean, just like this, we've got like 500-600 unit tests generated for us, and they're going to be different every time. So the more we run this, the more value we actually get. So I don't know if anyone's ever dealt with randomized testing, like monkey testing a UI or fuzzing an application, but the responses you get are most of the time garbage. I don't care that 6,000 clicks down the line you made my application crash, and then you give me all 6,000 of those clicks. That's not really relevant to me when I'm trying to debug this application. So now I need to spend time debugging the information it gives me. So these property-based testing libraries, and Scala does this particularly well, they'll shrink the input to the smallest form before they give you the response. So they'll decrement integers and find the smallest integer that makes that property fail. They'll remove items from lists and find the smallest list size that'll make a property fail. They'll remove characters from strings. They'll do all of these things. And they'll try to give you the minimal input that makes your test fail. So it's pretty useful. So here's a quick example of a test that you think would pass. I take a character, I convert it to uppercase, I convert it to lowercase, and then I check that that's equivalent to simply converting it to a lowercase. So we run it through a property-based testing for all strings, and look at the failing input. I mean, that failed, okay, I don't really know why. But the minimized input's a single character. And a nice thing with property-based testing is once you find a failing test case, you can run it multiple times and get different minimized inputs, and you can kind of start to see patterns from the inputs that it failed with. So we can look at these three minimized failed inputs and notice that they all kind of have an apostrophe above the letter. So by Googling about this, we can find that these Unicode characters don't have a valid uppercase representation. So they'll lose information when they go to uppercase and back to lowercase. So we wouldn't really be able to identify that without the shrinking. So that's pretty cool. So conclusions. Once you start doing these property-based tests, you can kind of get enamored and feel a false sense of security from thousands of passing tests. Your properties can be kind of pointless, and then you get 10,000 passing tests, and you've proven nothing about your code. So for this case, it kind of works well with unit testing, and I wouldn't say it's about to replace unit testing anytime soon, but there's definitely some patterns that are more applicable to property-based testing than unit testing. And this is from the creators. They say, run small tests often instead of large tests infrequently. So on your properties, test, run 100 on each property. Don't run 10,000 or don't run 100,000 just because you can. The reason for that is it takes quite a while, so you'll be discouraged from running them as frequently. But more importantly, the shrinking algorithms don't work as efficiently with large inputs. They'll be able to shrink a smaller input a lot more effectively. So, yeah. Yeah, any questions?
Yeah, I have one question and one comment. The question is, in practice, do you find yourself using property-based testing more in kind of like testing single units or in testing like the integration of production things?
Well, I always start out testing single units, and then my properties kind of grow into integration-based tests. So like it depends on what level you start at. Generally, you can find applicable properties for a single unit of work, but I feel it's really valuable when you start talking about the entire system in play. So in practice, I guess it's a little bit more applicable to integration, but it covers units quite well as well.
Okay.
I mean, I guess in that situation, I would just say it's more difficult to test a single function for these properties than it is to test a system, because it's really easy to say things about a system. It's hard to say these same things about a single unit of work.
Okay.
So, yeah.
And another comment about the Oracle test. I kind of got the feeling that it's sort of dangerous because you want to test a lot of times. When you find a bug, is maybe some aspect like you never think of. Then if you use some kind of legacy code or a alternative algorithm to test to run tests against your new code, maybe that kind of bug is not adequately captured.
Yeah, definitely, which is why any of these weird situations, definitely run a unit test for it. Don't think that randomly these really complicated edge cases are going to get found. But by running small amounts of tests frequently, you'll find that the range gets covered pretty quickly. So, yeah.
Just one comment, which is for those interested in property-based testing and this kind of stuff, TrackLevel's website has another library in addition to Scala check called Discipline for law checking. Follows sort of similar principles to be able to define laws for type classes, and you can sort of check them. The other point is there are two different ways or strategies, and in Haskell there is quick check and then there's small check. And I believe there's a Scala code for that, though I don't know how well maintained or not it is. But the idea is not to pick sort of random distributions, but to go with the premise that so this is sort of a small model hypothesis for bugs, that if there's going to be a bug, there's usually a small example which would result in that bug. And so exhaustive checking for up to a certain depth or up to a certain level will usually trigger the bugs, and that's what it does. Instead of doing random testing, random generations, it will exhaustively check up to a certain limit that you specify. So that's sort of a dual technique, and both of these together are sort of useful.
Definitely. More to that, I mean, I didn't really talk too much about it, but you'll find that property-based testing definitely changes the way you look at your types, and you'll find yourself defining a lot more types instead of just using primitives more so. So like instead of accepting an age, an integer for an age, you might want to define an age type, and then you can have a generator for this age type. And it's going to more frequently generate applicable value to your test. So don't take a string for an email, have an email generator, and expect emails to propagate through your application. And then you can start having a lot more value. Yeah, randomly testing these things without defining new types might not be so good.
Yes, question. I know you talked about that. And one thing is that generating your custom types, how would you do that? As in, how would people do that, especially for finding the thinking? So, because it was fun,
I honestly haven't dealt too much with generating custom types, but most people just have a for comprehension, and it all boils down to primitives at some point. So it'll use the same shrinking algorithm on these primitives on your data types, and it'll shrink those attributes of your type. So they kind of use a for comprehension. Let's say you have a person, then you'll have age, and it'll choose a certain value. Then you'll have a string, and it'll choose a certain value, and then it'll yield that person, and now you have a person generator. And that's kind of how it works. It's a little bit more complicated than that. There's actually quite a few great resources. There's a really good presentation right here called Scala Check Magic, and it's like 50 minutes, and they pretty much only talk about generating your custom generators in Scala. So I definitely recommend checking that out if you want to learn more about generating.
So how about say, I'm just curious, how about say, generating custom type or generating custom functions?
Absolutely. Yeah, I can't believe I forgot about talking about that. As long as you're writing purely functional code, a function is just a lookup in a table. So you can definitely generate these. You can give it a type signature, and it'll start generating functions that match that type signature.
I guess the way to generate functions is similar to generating custom type, or it's different.
Yeah, I'm not 100% sure on that one.
Okay.
Yeah.
Can you use like a Scala check to do an exhaustive search? Like if you have a type that is, the space isn't that big?
Sure. I mean, you can tune how many options it actually uses. I've actually never thought about it that way. It might not be the best tool because it is kind of driven by this random generation. If you have an exhaustible range, I mean, you could just kind of write a test for each of those, or a loop or something. I'm sure it could be used for that, though. Yeah, that's a good point.
It has.
And then you have it does?
Assuming I'm remembering correctly, it has things like for all and stuff like that, or maybe.
Well, it has for all, but it's just going to randomly choose based on a range.
But if it's an enumeration, you can pick it automatically, right? If it's an exhaustive thing, it's essentially in some sense an enumeration.
Yeah, that makes a lot of sense, actually. Yeah. I really doubt that it would randomly, it would probably pick up on that, actually. But yeah, in that case, you actually have a proof, which is cool.
How about speed of those tests? So if you introduce a property-based test, how longer does it take to run those speed of the testing?
As long as you keep the default range to a reasonable amount, like 100, it's not that long. I mean, it's pretty well equivalent to unit testing. I haven't noticed any particular delay when running it. However, I haven't had a system large enough that I can really take benchmarks on it. But as long as you are keeping the amount of cases it checks on each property sane, it should be fine. Cool. All right, thanks everyone.